lecture 21, and I want to start with a brief outline. So what we will do is we will learn about angular speed, and then we will do standard examples of angular speed, which is an object that changes its moment of inertia. And then we will revisit neutron star. This is basically just to complete our discussion and also to show you that the same simple physics also applies to an object that is much larger than, let's say, my chair. Okay, so physics applies from across scales, from electron orbits to the orbits of planets. Okay, and then after that we will do Kepler's second law, and then we will finish with gyroscopic precession. Okay, before we continue, let's revisit angular momentum. Angular momentum is given by this formula here. The symbol is L. Angular momentum L is equal to moment of inertia times the angular speed. And then for a system, for any system, the net torque is equal to the change of angular momentum over time. This should remind you of the force is equal to the change of momentum vector over time, right? So very similar. And then for a system where, so if torque net is equal to 0, that means the angular momentum is conserved, right? Because the derivative of a constant is equal to 0. Good. So far we just do review. Next, let's do practice problem. So this is fairly straightforward problem. Here we will do conservation of angular momentum. Basically, angular momentum of before is equal to the angular momentum of after. So I naught times omega naught is equal to I final times omega final, where I is the moment of inertia and omega is the angular speed. Okay. All right. Before we do Q3, I promised in class earlier today that I will show you a video of experiment with the Hoberman sphere. So let me switch to different camera. Okay, let me start.
This is a Hoberman sphere. You can expand it and contract it using this string. What I'm going to do is to use it to demonstrate the conservation of angular momentum. The axis, I'm going to rotate it about this vertical axis, and that axis is also denoted by the string that passes vertically through the sphere. We will note first that the moment of inertia in this expanded configuration is much larger than the moment of inertia in this contracted configuration. So what we can expect is that if we give it some angular momentum in the expanded high moment of inertia configuration, and then we contract it, its angular speed should increase. And sure enough, it's one of the most spectacular demonstrations, I think, of conservation of angular momentum. This is a
All right, that's Dr. Boyd, and you can find, or Dr. Boyd Edward. So Dr. Edward, you can find the video on YouTube. Now let's go back to our notes. So we have this problem here. A student is spinning in a swivel chair with weights extended. Their moment of inertia initially is 3 kg per meter square. They spin at omega naught, which is equal to 30 RPM. They pull their arms in, reducing their moment of inertia to 2.5 kg meter square. What is their new spinning rates? Okay, so if you want to do it, you can pause the video, but I'm just going to do it somewhat fast here. Basically, the moment of inertia before is equal to the moment of inertia after, right? And then this one is equal to I naught times omega naught is equal to I final times omega final. And what is being asked is omega final. So omega final is equal to I naught divided by I final times omega naught. Okay. All right. Now we are ready. So this is the answer in terms of the analytical formula. Before we put the number, it's good to check what is the unit of the option. The unit of the options are in RPM. The options are in RPM, so we don't need to convert RPM to radian per second, which makes our life easy. So this one, I naught is equal to 3. I final is equal to 2.5. Omega naught is equal to 30. 30 divided by 2.5 is 12. So 3 times 12 is 36 RPM. Okay, fairly straightforward. The next one, we did it in class, so I'm just going to do it really fast. A spinning figure skater, again, here it doesn't have to be figure skater. It can be electron, it can be Hoberman sphere, it could be a neutron star, right? A spinning figure skater pulls their arms as they rotate on the ice. As their arms come in, what happens to their angular momentum L and kinetic energy K? So we know that K stays the same. So I'm just eliminating options that says K doesn't stay the same. So now the answer is either B, D, or D, F. Right? Next, in class, we learned that for a system that change its moment of inertia, so a spinning system that change its moment of inertia into smaller, then the energy increases. So one example is a spinning figure skater or spinning Hoberman sphere. When we change the configuration from high moment of inertia to small moment of inertia configuration. So the answer is also B. Right? All right. So next we will talk about neutron star. We learned in the class that neutron star is what happened when a star, let's say our sun, collapse into basically dead star because it runs out of fuel. So let's say our star starts at R naught and then shrink to the size of a city. But here, this problem here, the size after the final size is 1/50th of the original size, so 50 times smaller. So R final is equal to, okay. So in class we discussed that the reason why we call this neutron star because of the how compact this dead star is. The protons and electron collapse and behave like neutron. This is why we call it a neutron star. It is an oversimplification, but I hope it paints the picture physically. And in class, I sketched the way to do it. So we start with conservation of momentum, which is here. And we note that this is interesting. Let me just go through it with you. Maybe that's easier. So first, we know that when a star, let me change, a star change its size, then the moment of inertia also change. Right? The mass stays the same, but the radius changes. So the moment of inertia is given by 2/5 times m times r square. And the radius is smaller by a factor of 1 divided by 50,000. There is no external torque. There is no invisible hands that makes it spin slower or faster. So the angular momentum stays the same. And it is equal to moment of inertia times angular speed. Moment of inertia change, but the mass stays the same, so m cancels, and this prefactor also cancel. And then we get the ratio between omega final and omega naught, which is given here. Right? So this is the analytical formula of the answer. Okay. And then when we put the number, we get this number here. The angular momentum after the star shrinks is 2.5 times 10 to the 9th, the initial angular, not angular moment, angular speed. So the final angular speed is equal to 2.5 times 2.5 billions times the initial angular speed. And then next, we need to use this formula, omega is equal to 2 pi times period. Okay. Okay, this is just the angular speed. Basically, the time to travel at displacement angle equal to theta is 1 period, because 2 pi is the angle of a circle, and the time to travel the distance, not the distance, the displacement angle equal to 2 pi is the period. Okay, so we need to use the formula here, which is the same as this formula here. Okay, and then if you know omega, the ratio of omega, so now what this notes does is to express the left-hand side, the right-hand side of this equation, and then move it to the left-hand side. And omega final is equal to 2 pi divided by the final period. And here 2 pi cancels. And then T naught is given. T naught is basically 27 days. With that, you can compute T final. Okay. All right, so T final is about on the order of 1 millisecond. So basically this dead star or neutron star rotates 1,000 times per second, and we call that pulsar because it generates pulse at radio frequency. Okay. All right, so next let's do something fun. The next topic is Kepler's second law. So there are a lot of history in physics. So for Kepler's second law, there are many people that made contribution before Kepler came up with that law. I wrote it here. Sorry. Yeah. So this person here, Tycho Brahe, spent decades gathering planetary data. Kepler spent 40 years reducing it to 3 laws. So it's quite an amazing story. But let's return to our in-class worksheet. So basically it says that, let me just read it. The imaginary line joining a planet and the sun sweeps out equal areas of space during equal time. So over a given time, the area that I'm drawing here, they are always equal, okay? There is more involved derivation. So basically what I'm trying to sketch here is that calculating this area here, which is equal to or approximately is the area of a triangle. I know this is not straight here. So basically it's half times the area of rectangle, and this is the area of rectangle. And then dr is equal to v dt, and from that you can get this formula here, okay? And the fact that dA is constant, that means the angular momentum along this path or the elliptical orbit is also constant. Okay, so the calculation involved mathematics, and it's actually beautiful, but you guys have taken Physics 121. There is an easier way to conclude that the angular momentum is always constant, okay? So you need to, one way to do it is you need to notice that the force or the gravitational attraction between two objects is always along the line that connects their center of masses. There is a name for this type of force. The name is central force. So the name is not important, but what is important is that because the force is along the line of this lever arm, that means torque is equal to this formula here, and sine theta is equal to 0 because it's sine 0 degree, right? So that means the net torque is 0, which implies that the angular momentum is constant, right? So instead of using math, we use physics. We can easily show that for central force, or because gravitational force is a central force, then there is no torque. Because there is no torque, then the angular momentum is constant. Okay. All right, so that's all that you need to know. And then we have this Q5, and I'm gonna move myself to the top. All right, so a planet P moves around the sun S in an elliptical orbit. Neglect all forces except gravity. As the planet moves from aphelion, which is the furthest distance between the planet and the sun, as the planet moves from the aphelion to perihelion, perihelion is the closest distance between a planet and the sun, its angular momentum about the center of the sun is, okay, you can pause and answer, but based on what we learned, the angular momentum is always constant, so the answer is remain the same, right? The answer is D. Okay? Good. Next, we have this question here. As the planet moves around the sun in an elliptical orbit, as the planets move from aphelion to perihelion, its speed changes from VA to VP. Given the distances RA and RP, which relationship is correct? Okay, so first, again, using Kepler's second law, we know that L is constant. And here we only care about the magnitude, so we can even say this if we want. So M times V aphelion times the distance, which is RA, times sine theta is equal to the distance from the closest distance to the sun, which is RP, not RB, RP, times M times VP times sine theta P. So M cancels. All right, so if this is an elliptical orbit and this is the planet, the lever arm is here. This is RP. This is RA. One thing that you notice is that the speed is at this point is perpendicular. Okay, so theta A here. So this one is theta A. This is theta B. Theta A is equal to 90 degrees. Theta B is equal to 90 degrees. So this one is equal to 1. This one is equal to 1. So RA times VA is equal to RP times VP. And then this question asks for VA. So this is equivalent to VA is equal to VP times RP divided by RA, right? So the answer is VP, RP. The answer is D. Oops. Let me remove myself. Apologize for that. So one critical point is that theta A here and theta B here, they are perpendicular from the lever arm. Okay. Because of that, then sine theta A and sine theta P is equal to 1, and that makes the math very simple. All right, so we can, let's see. So this is the lecture notes right now, and the answer is D. Just want to make sure that I don't miss anything. So next is we will talk about gyroscopic precession. So gyroscopic precession will not be part of exam 3 and final exam, so don't worry too much. But it's actually really a remarkable system. So basically we have a gyroscope. So it looks like this gyroscope. So if the gyroscope doesn't spin, I'm gonna play the video.
Wheel, just like so. And I let it go. Well, we all know it will happen. Clunk. It's clear. All right.
All right, so if there is no force, then the gyroscope, if you mount the gyroscope, then it will just fall down, right? So that's obvious. But one thing is interesting when it spins, and I'm gonna show you a video. So this is, of course, not me. This is a lecture by Walter Lewin. He teaches physics, or he taught physics at MIT, or he still teach, I don't know, but he's one of the legend in the field. So let me show you.
Torque is like this. It goes.
So first he spins the gyroscope. It doesn't have to be this fast, like fast spinning gyroscope, and then he mounts it on
And there it goes.
the axis, and then instead of
About
falling
10
down,
seconds.
it precesses. It rotates.
Isn't that amazing? And it rotates seen from below clockwise. Now it's going this way, and I'm going to redo the experiment, changing the direction of rotation, and then it will go the other way around. So now the angular momentum, is it rotating like this, is pointing here. Spin angular momentum is pointing like this. Torque is like this. And so the spin angular momentum is chasing that torque. I'm the spin angular momentum, I'm the torque. This is the torque. It's chasing it.
So you can...
All right, so I have this in my right hand.
You can finish watching this video yourself, or maybe we can speed up to where he changed the position of the probe, and you will see that the gyroscope will rotate the opposite way.
It's now in this direction. See, it's turning the other way around. Angular momentum is in this direction. Torque is now.
So I like this video, but there is a better explanation of gyroscope. So this is a famous channel. Which, the name of the channel is Veritasium. And we will play this video for about 2 minutes, so be patient. And then that's the end of this video lecture, okay?
Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
All right, so that's all that we have for lecture 21. But briefly, we started with a recap of connected motions of linear and rotation motion, and we use Atwood machine with pulley with mass capital M. And then one thing for that type of problems, what you need to be careful is the sign of alpha and A, which you need to designate yourself. And then we talk about angular momentum is R cross P. And then for angular momentum of a rigid body is moment of inertia times angular speed or angular velocity. And then the change of the angular momentum is equal to torque. And for a system that doesn't have torque, like rotation of evolution of our planet around the sun, then the angular momentum is constant. But for a system with torque, like in the gyroscope, then the angular momentum is not constant. Okay. If you have any question, please stop by our office hours or just email us. Okay. And enjoy your extra 1.5 hours this Thursday. See you on Tuesday.